Imagine the universe at its very beginning, not as the vast star-filled expanse you picture now, but as something impossibly small, smaller than a grain of sand, hotter than a million suns, holding everything that would ever exist, stars, galaxies, planets, you, me, all compressed into a single point, infinite in density, brimming with potential. Then, in a fleeting moment, it began to grow, not slowly or steadily, but with a speed beyond comprehension, a burst of expansion that shaped the cosmos we know. This is the mystery of cosmic inflation. What was it? What drove it? Let's drift into this enigma together and let the stars cradle your thoughts. Picture the universe now, just a fraction of a second old, a seething sea of energy, too dense to describe, too chaotic to imagine. Something extraordinary happens in this moment. In less than a trillionth of a second, the universe expands, not just a little, but by a factor of billions. Space itself stretches faster than light, faster than time can measure. This breathtaking leap is what we call cosmic inflation, as if the universe took a deep breath and grew into the vastness we see today, setting the stage for everything that followed. Why does this moment matter? Why should we care about something so distant, so fleeting? Because inflation is the sculptor of the cosmos. Without it, the universe might have been a very different place, uneven and lumpy, with some regions too dense and others too sparse. Stars might never have formed, galaxies might never have spun into being. But our universe is smoothed, almost perfectly balanced, like a calm sea under starlight. Inflation made it so, stretching space so quickly that any wrinkles were ironed out, leaving a canvas vast and uniform, ready for the first sparks of creation. Let's linger in this idea, floating in that early universe, weightless, surrounded by infinite potential. The energy of inflation hums around you, a soft vibration, like a lullaby sung by the cosmos. It's comforting to think that everything we know, every star, every planet, every dream, began in this single miraculous moment. Cosmic inflation is not just a scientific concept. It's a story of beginnings, a tale of how the universe became a place where life could one day emerge, where you could one day exist. Now let's explore the science, gently, like turning the pages of a bedtime story. Scientists first imagined cosmic inflation in the 1980s, when a physicist named Alan Guth proposed a bold idea. He wondered how the universe could be so smooth, so flat, when it started in such chaos. His answer was inflation, a sudden explosive growth in the universe's earliest moments. Imagine blowing up a balloon, but instead of air, it's space itself, expanding faster than you can blink. This growth, Guth suggested, happened between 10.36 and 10.32 seconds, after redacted seconds after the Big Bang, a time so small it's almost beyond imagining. What caused this expansion? That's where the mystery deepens, like a dream you can't quite grasp. Scientists think a strange force called the inflaton field might have driven it, an invisible energy field, filling the early universe, pushing space apart. Picture it as a gentle tide, swelling the cosmos, then fading away, leaving only traces in the stars. But what was the inflaton? Was it a particle, a force we've never seen, or something entirely new? We don't know. And that's what makes this question so beautiful, a puzzle floating in the cosmic night, waiting for us to solve. The evidence for inflation lies in the sky, in the faint glow of the universe's first light, known as the cosmic microwave background, or CMB. It's like a snapshot of the cosmos when it was just 380,000 years old, a map of ancient warmth. In that light, scientists have found patterns, tiny ripples, like whispers from the dawn of time. These ripples, they believe, were born during inflation, when quantum fluctuations, little flickers of energy, were stretched across the universe. The CMB shows a universe, almost perfectly smooth, but not quite, just as inflation predicts. Imagine those ripples, now dancing across the sky, etched in light older than the Earth. They're a clue, a gentle hint of inflation's work. Scientists have studied them with telescopes like the Planck satellite, mapping the universe's baby picture. What they've found fits the story of inflation remarkably well. The universe is flat, its geometry balanced, its structure seeded by those ancient fluctuations. It's as if the cosmos is whispering to us, telling us inflation was real. It's still holding back its secrets, inviting us to wonder. The mystery grows deeper, like a dream that shifts as you fall asleep. If inflation happened, what started it? What lit the spark? Some scientists propose it was a random quantum event, a flicker in the chaos of the pre-universe. Others imagine a multiverse, countless other universes, each with its own inflation, its own story, picture bubbles of reality floating in an infinite sea, each one a universe like ours, or utterly different. It's a thought that stretches the mind, a cosmos vast beyond words, and we're just one part of it. Rest in this idea, adrift in that multiverse, weightless, surrounded by countless realities. Each one hums softly a different song, a different sky. The concept of a multiverse is both thrilling and humbling, suggesting our universe is one of many, each born from its own moment of inflation. But whether this is true, we don't know. Question lingers, soft, like a whisper in the dark, inviting us to imagine possibilities beyond our reach. Did inflation happen everywhere, or just in our corner of the cosmos? Could it happen again, reshaping the universe anew? Scientists are searching for answers, listening for echoes of inflation in gravitational waves, ripples in space-time itself. Experiments like the Simons Observatory and the future Lightbird satellite are tuning their ears to the cosmos, hoping to hear that ancient song. For now, the answers drift just out of reach, like a dream you'll chase another night. Let's not chase them tonight. Let's float in the mystery of cosmic inflation, picturing the universe, newborn, expanding in a heartbeat, stretching into infinity. It's a story of beginnings, of possibilities, of a cosmos that grew to hold you, me, and every star you ever seen. What drove it? We may never know, but the question itself is enough. A gentle lullaby from the stars, soothing you into rest. Cosmic inflation reminds us how little we understand, yet how much we can wonder. It's a mystery that connects us to the universe's first moments, to the forces that shaped reality itself. As we explore this idea, we're not just learning about the cosmos, we're touching the edges of existence, feeling the pulse of creation. The inflaton field, the CMB ripples, the multiverse, they're all part of a story that's still being written. A story you're part of, even as you drift towards sleep. Think of the scientists gazing at the CMB, piecing together clues from light that traveled for billions of years. Their work is a quiet pursuit, a meditation on the universe's origins. They don't have all the answers, and neither do we, but that's what makes this mystery so comforting. It's okay not to know. It's enough to ask, to imagine, to let the question rest beside you, like a star in the night. The beauty of cosmic inflation lies in its balance of the known and the unknown. We know the universe expanded, that it's smooth and flat, that ripples in the CMB hint at its past, but we don't know why or how or what came before. This balance is a gift, a reminder that the universe is both familiar and strange, a home and a mystery. As you listen, let this balance soothe you. Let it carry you toward dreams. What is cosmic inflation? It's the universe's first breath, its moment of becoming. It's a question that invites us to wonder, to float in the vastness of the cosmos, to feel connected to something greater. As we leave this mystery behind, let your thoughts soften. Let them scatter like stardust. The universe began with a burst of inflation, and now it holds you gently in its embrace. Rest now and dream of that moment when everything began. Another mystery awaits, but for now, just drift. Imagine the universe in its earliest days, long before the galaxies we know, before the planets, before the Earth. Picture a vast, dark expanse, a cosmic night without a single star to light the way. The universe is young, just a few 100 million years old, filled with swirling clouds of gas, drifting in silence. Then in this darkness, something miraculous happens. A faint glow appears, then another and another, until the void begins to sparkle. These are the first stars, the universe's earliest lights, igniting the cosmos. But where did they come from? How did they form? Let's drift into this gentle mystery, letting the stars guide us towards sleep. Close your eyes and imagine that early universe, a place of quiet potential, where the only ingredients are hydrogen and helium, the simplest elements, born in the Big Bang's fiery embrace. These gases float in vast clouds, stretching across the cosmos like a misty sea. The universe is still, cooling from its explosive birth, and there are no stars, no galaxies, just this endless darkness we call the cosmic dark ages. Yet, within this darkness, the seeds of light are waiting, ready to spark the first stars into being, to transform the universe forever. Why does this moment matter? These first stars, known as population 3 stars, were the architects of the cosmos. They didn't just light up the darkness, they changed the universe's story. Their blazing hearts forged heavier elements: carbon, oxygen, iron, the building blocks of planets, of life, of you and me. Without these stars, the universe might have remained a cold, empty place, devoid of the galaxies we see today. Their birth was a turning point, a moment when the cosmos began to shine, setting the stage for everything that followed. Let's linger in this thought, floating in that dark, quiet universe, surrounded by clouds of gas, each one humming with possibility. It's a comforting idea, isn't it? That the stars we love, the ones we wish upon, began with these ancient lights, born in a time so distant it feels like a dream. The first stars are a reminder that even in the darkest moments, light can emerge, gentle and unstoppable, carrying the promise of creation. Now let's explore the science, softly, like whispering a story under the night sky. After the Big Bang, the universe expanded and cooled, leaving behind clouds of hydrogen and helium, held together by gravity. These clouds were massive, far larger than the stars we know today, and they floated in a universe without metals, without dust, just pure primordial gas. Scientists believe that somewhere, around 100 to 200 million years after the Big Bang, our gravity began to work its magic, pulling these clouds tighter, compressing them until they grew hot and dense enough to ignite. What sparked this ignition? That's where the mystery begins, like a question whispered by the cosmos. Unlike modern stars, which form in dusty, metal-rich clouds, the first stars had only hydrogen and helium to work with. They were giants, hundreds of times more massive than our sun, blazing with a fierce, pure light. Scientists call them population 3 stars, the third generation in a naming system that counts backward. These stars were so massive, so hot, that they burned through their fuel in just a few million years, a fleeting moment in cosmic time. Imagine one of these stars forming, a cloud of gas collapsing under its own weight, growing denser, hotter, until its core ignites in a burst of fusion. Hydrogen atoms smash, together fusing into helium, releasing energy that lights up the darkness. This is the birth of a star, a moment of creation that echoes across the universe. But how did these clouds collapse so perfectly? What conditions allowed them to form? The details remain elusive, like a dream that fades as you wake. But scientists have theories, pieced together like a cosmic puzzle. They believe tiny fluctuations in the early universe, ripples, left over from the Big Bang, acted as seeds for these clouds. Gravity pulled gas into these denser regions, creating clumps that grew over millions of years. But the process was delicate, requiring just the right balance of temperature, density, and turbulence. Too hot, and the gas would scatter. Too cold, and it wouldn't collapse. The universe had to find its rhythm, a gentle dance of gravity and gas, to birth its first stars. We can't see these stars directly, not yet, because they burned out long ago, their light scattered across billions of years. But their legacy lingers in the cosmos, in the elements they created, in the galaxies they helped form. When population 3 stars died, they exploded in massive supernovae, scattering heavier elements into space. These explosions seeded the next generation of stars, the ones that built galaxies, the ones that made our sun possible. Every atom in your body, every breath you take, carries a trace of those first stars, a quiet connection to the universe's dawn. The mystery deepens when we ask where these stars formed and why we haven't found them. Scientists are searching, using the most powerful telescopes like the James Webb Space Telescope to peer back to the universe's earliest days. They hope to catch a glimpse of these stars' light, or at least the glow of the galaxies they sparked. But the universe is vast, and time is deep, and finding these ancient lights is like searching for a single candle in an endless night. The challenge is part of the wonder, a reminder that some questions take time to answer. What conditions shaped these stars? That's another piece of the puzzle. Scientists use computer simulations to recreate the early universe, modeling how gas clouds collapsed, how turbulence and gravity interplayed. These simulations suggest that population 3 stars formed in small clusters, in regions where gravity won over chaos. But the models aren't perfect. Some predict stars even more massive than we thought. Others suggest they formed in pairs, dancing together in the dark. The truth lies somewhere in these ideas, waiting to be uncovered. Another question lingers, soft and intriguing. Did these stars form everywhere at once, or in pockets scattered across the cosmos? The universe was vast even then, and some regions may have stayed dark longer, while others lit up quickly. The timing matters, because the first stars didn't just shine. They transformed the universe. Their ultraviolet light ionized the surrounding gas, turning it from neutral to charged, a process called rionization. This cleared the cosmic fog, letting light travel freely, making the universe transparent as it is today. Imagine that moment, the universe waking up, its darkness pierced by countless stars. It's a beautiful thought, a reminder that light always finds its way. But we don't know how long reionization took, or how the first stars drove it. Some scientists think it happened quickly, a sudden burst of light. Others imagine a gradual dawn, stretching over millions of years. The James Webb Space Telescope is searching for clues, looking for the faint glow of early galaxies, hoping to map this cosmic sunrise. The mystery of the first stars is also a question of connection. If we find them or their remnants, we'll learn not just about the universe's past, but about our own origins. Every element heavier than helium in your body, carbon, nitrogen, oxygen, was forged in the hearts of stars. Many of them, those first, massive population 3 stars. Their supernovae spread these elements across space, seeding the clouds that formed our sun, our planet, our bodies. In a way, we are their children, carrying their legacy in every cell, every breath. Where did the first stars come from? They came from the universe's quiet potential, from clouds of gas shaped by gravity, from ripples born in the Big Bang. But the detail, how they form, where, when, remain a gentle enigma, a question that invites us to wonder, to dream. Scientists will keep searching, peering into the cosmos's deepest, past, and one day we may see their light, or the echoes of their explosions shining across billions of years. As we leave this mystery, let your thoughts soften like starlight, fading at dawn. The first stars lit up the universe, and their legacy lives in you, in every breath, every dream. They remind us that even in darkness, light emerges, gentle and eternal. Rest now and imagine those first stars sparkling in the cosmic night, guiding you towards sleep. Another mystery awaits, but for now, just drift. Imagine a moment before time, before space, before anything at all. Picture the universe, not as the vast star-filled cosmos you know, but as a single point, infinitely small, infinitely dense, holding all that would ever be. Every galaxy, every planet, every dream you've ever had. Then, in an instant, it bursts into being, expanding, unfolding, creating everything. This is the Big Bang, the moment our universe began. But what caused it? What sparked the greatest beginning of all? Let's drift into this gentle mystery floating in the quiet wonder of the cosmos, letting the stars guide us toward sleep. Close your eyes and imagine that singular point, a place where everything is compressed, where time and space don't yet exist. It's not a place you can see or touch, but a state of infinite potential, a seed of reality. Then, around 13.8 billion years ago, something happens. The point expands rapidly, violently, filling the void with energy, matter, and the beginnings of time itself. This is the Big Bang, not an explosion in space, but the creation of space, the birth of the universe. It's a moment so profound it feels like a story whispered by the cosmos. Why does this question matter? The Big Bang is more than a scientific event. It's the origin of everything we know, the root of every star, every breath, every thought. Understanding what triggered it could unlock the deepest secrets of existence, revealing why there is something rather than nothing. It's a mystery that connects us to the universe's first heartbeat, a question that feels both vast and intimate, like a lullaby sung by the stars, soothing us as we wonder. Let's linger in this thought, floating in that moment before the universe began. Weightless, surrounded by infinite possibility. It's a comforting idea, isn't it, that everything, every light in the sky, every moment of your life, traces back to this single miraculous spark. The Big Bang is a story of creation, a tale of how nothing became everything. And asking what triggered it is like asking why we're here. A question that invites us to dream. Now, let's explore the science gently, like tracing the edges of a bedtime story. The Big Bang theory tells us the universe started hot and dense, then expanded and cooled, forming the cosmos we see today. Scientists have mapped its history through the cosmic microwave background, a faint glow of ancient light that carries echoes of the universe's infancy. They've traced the universe's growth from a soup of particles to the galaxies we know. At the moment of the Big Bang itself, what caused it remains a mystery, shrouded in the mists of time. What could have triggered such an event? That's where the wonder deepens, like a dream you can't quite hold. The Big Bang marks the beginning of time as we know it. So asking what came before is like asking what's north of the North Pole. Time and space were born in that moment, making the idea of a before difficult to grasp. Yet scientists speculate, weaving theories like stories told under starlight. Some suggest the Big Bang was a quantum fluctuation, a random ripple, in a sea of nothingness, sparking the universe by chance. Imagine that for a moment. A universe born from a flicker, a tiny twist in the fabric of reality. Quantum mechanics tells us that even in empty space, particles can pop into existence, fleetingly, before vanishing. Perhaps in some pre-universe state, a quantum event grew uncontrollably, becoming the Big Bang. It's a strange, beautiful idea, suggesting our universe might be one of countless fluctuations, a single note in an infinite symphony. But we don't know if this is true, and the thought drifts like a whisper in the cosmic night. Another idea is the multiverse, a concept that stretches the mind like a dream within a dream. Picture countless universes, each with its own Big Bang, floating in a vast, unseen sea. Our universe could be one bubble among many, each born from its own spark, its own rules of physics. Some theories suggest our Big Bang was triggered by a collision between universes, or a tunneling event where our universe emerged from another. It's a story of infinite possibilities, where our reality is just one chapter in a cosmic book. Let's rest in this thought, imagining a multiverse, each universe glowing softly like stars in an endless sky. The idea is both humbling and comforting, suggesting we're part of something far greater, something eternal. But the multiverse is just a theory, untested, unproven, a question mark hanging in the cosmos. We don't know if other universes exist, or if they could explain our Big Bang. The mystery remains, inviting us to wonder, to float in its gentle embrace. Some scientists propose a different approach, suggesting the Big Bang wasn't a beginning at all, but a transformation. Picture the universe cycling through phases, collapsing and rebounding in a series of Big Bangs, each one a fresh start. In this cyclic model, our Big Bang was triggered by the collapse of a previous universe, a cosmic phoenix rising from its ashes. It's a poetic idea, a universe reborn again and again, but it's hard to test, and the details slip away like a fading dream. Another theory involves cosmic inflation, a rapid expansion that happened just after the Big Bang. Scientists believe this brief explosive growth smoothed the universe, setting the stage for galaxies to form. But what caused inflation, and did something trigger both it and the Big Bang? Some propose an inflaton field, an energy force that drove expansion, but its origins are unknown. The Big Bang and inflation are intertwined like threads in a cosmic tapestry, but the spark that started it all remains hidden. The evidence for the Big Bang is strong, etched in the universe's oldest light. The cosmic microwave background shows a universe that was once hot and dense, expanding steadily for billions of years. The abundance of light elements like hydrogen and helium matches predictions from the Big Bang's fiery birth. Even the universe's large-scale structure, galaxies clustered in a cosmic web, bears the imprint of that first moment. But the cause, the trigger, lies beyond our reach. A question that feels both scientific and philosophical. Imagine the scientists pondering this mystery, gazing at star-filled skies, their minds drifting to the edge of time. They use mathematics, particle accelerators, and telescopes to probe the Big Bang's echoes, but the moment itself resists their grasp. It's a humbling pursuit, a reminder that some questions are too vast for answers, at least for now. Yet the search is soothing, a quiet meditation on existence, connecting us to the universe's deepest roots. What triggered the Big Bang? It might have been a quantum flicker, a multiverse event, a cyclic rebirth, or something we can't yet imagine. The truth lies in the shadows, waiting for a new theory, a new discovery to light the way. For now, the question is enough, a gentle enigma that invites us to wonder, to feel the universe's vastness, to rest in its mystery. It's a story of beginnings, of a cosmos born from nothing, carrying us all in its embrace. The beauty of this mystery lies in its openness, its refusal to be solved. We know the universe began, that it expanded, that it grew to hold stars and galaxies and life. But why it began, what set it in motion, remains a whisper from the cosmos, a question that soothes as much as it intrigues. As we explore this idea, we are not just seeking answers. We are touching the edge of reality, feeling the pulse of creation itself. Think of the universe now, stretching across billions of light years, filled with light and wonder. It all traces back to that single moment, that spark we can't yet name. The Big Bang is a reminder that beginnings are mysterious, that the unknown is a place of possibility, a place to dream. As you listen, let this thought comfort you. Let it carry you toward rest, like a star drifting in the cosmic night. What triggered the Big Bang? It's the universe's first question, its deepest secret. It's a mystery that connects us to the moment of creation, to the forces that shaped reality. As we leave this question behind, let your thoughts soften, like light fading into darkness. The universe began with a spark, and now it holds you gently in its vastness. Rest now and dream of that moment when everything began. Another mystery awaits, but for now, just drift. Picture a star, a glowing beacon in the cosmic night, burning steadily for millions, even billions of years. Its light travels across the universe, a quiet promise of warmth and energy. But then, in a fleeting moment, it erupts, blazing brighter than a galaxy, scattering its essence into the void. This is a supernova, a star's spectacular end, a cosmic firework that shapes the universe. But why do stars explode? What drives these gentle giants to such a dramatic finale? Let's drift into this soothing mystery, floating among the stars, letting their stories guide us towards sleep. Close your eyes and imagine a star, massive and radiant, its core a furnace where atoms fuse, creating light and heat. For eons it holds itself in balance, gravity pulling inward, the fire of fusion pushing outward. It's a dance of forces, graceful and eternal, lighting up the skies for planets and dreamers alike. Yet, within this star, a transformation is brewing. As it ages, its fuel begins to dwindle, and the balance falters. The star, once so steady, prepares for a final act, a brilliant explosion that will echo across the cosmos. Why does this matter? Supernovae are more than just cosmic spectacles. They're the universe's alchemists. When stars explode, they forge heavy elements: carbon, oxygen, gold, and iron, the building blocks of planets, of life, of everything we are. Without these explosions, the universe would be a simpler, emptier place, lacking the ingredients for worlds like ours. The mystery of why stars explode connects us to the stars themselves, to the forces that shaped our existence. A story as comforting as it is profound. Let's linger in this thought, floating in the glow of a distant star, feeling its warmth across the vastness of space. It's a gentle idea, isn't it? That the stars, in their final moments, give everything to the universe, scattering their gifts to create new worlds, new possibilities. Supernovae are a reminder that even endings can be beautiful, that destruction can lead to creation. A cosmic cycle that cradles us all. Now, let's explore the science, softly, like whispering a tale under a starlit sky. Stars shine because of nuclear fusion, where hydrogen atoms combine to form helium, releasing energy that keeps the star alive. For most of a star's life, this process is stable, but as the hydrogen runs low, the star evolves. In smaller stars, like our Sun, this leads to a gentle expansion into a red giant, followed by a quiet fade into a white dwarf. But for massive stars, those at least 8 times the Sun's mass, the story is different, leading to a cataclysmic end. Imagine a massive star, its core growing hotter and denser as it fuses heavier elements. Helium into carbon, carbon into oxygen, and so on, like a cosmic forge. Each stage burns faster, hotter, until the core reaches iron. Iron is the turning point, a stubborn element that doesn't produce energy when fused. Instead, it absorbs energy, disrupting the star's delicate balance. Gravity, which has held the star together for millions of years, suddenly wins, crushing the core in a fraction of a second. This collapse is the spark of a supernova. The core implodes, becoming incredibly dense, sometimes forming a neutron star or even a black hole. As the core collapses, the outer layers of the star crash inward, then rebound in a violent explosion, blasting material into space at speeds of thousands of miles per second. This is a core collapse supernova, a dazzling outburst that can outshine an entire galaxy for weeks. A star's final gift to the universe. But why do some stars explode while others fade? That's where the mystery begins, like a question whispered by the cosmos. Not all massive stars follow the same path. Some explode with predictable brilliance, while others behave strangely defying our models. Scientists study supernovae to understand the details, but questions linger. What exactly triggers the collapse? How does the explosion mechanism work? The process is so complex, involving neutrinos, shock waves, and turbulent gases, that even our best simulations struggle to capture it. Let's picture the moment of collapse. The star's core shrinking to a point smaller than a city, denser than anything we can imagine. Neutrinos, tiny particles that rarely interact with matter, pour out, carrying away energy. These neutrinos play a key role helping to drive the explosion, but their behavior is hard to predict. Some supernovae seem to need just the right conditions, a precise balance of density, temperature, and turbulence to explode. Others might fail, collapsing directly into black holes without a visible outburst. The line between explosion and implosion is delicate, a mystery we're still unraveling. Another type of supernova adds to the enigma, known as type Ia. These occur in binary systems, where a white dwarf, the remnant of a smaller star, orbits a companion. The white dwarf pulls material from its partner, growing heavier until it reaches a critical mass, about 1.4 times the Sun's. At this point, it ignites in a runaway nuclear explosion, obliterating itself in a brilliant flash. Type Ia supernovae are remarkably consistent, serving as cosmic yardsticks to measure the universe's expansion. But their exact triggers remain unclear. What pushes the white dwarf over the edge? Why do some systems explode while others don't? The mystery deepens when we consider the stars that defy expectations. Some supernovae are unusually bright, dubbed superluminous, lasting longer or shining with unexpected intensity. Others leave behind strange remnants, like neutron stars with odd magnetic fields. Scientists wonder if these are caused by unique conditions in the star's core, or perhaps by interactions with surrounding material. Each supernova is a puzzle, a snapshot of a star's final moments, and we're still learning to read their stories. Supernovae also shape the universe in ways we don't fully understand. Their explosions send shockwaves through space, compressing gas clouds and triggering new star formation. They scatter heavy elements, enriching the cosmos, but how much of each element is produced? The exact yields of supernovae, how much iron, oxygen, or gold they create, depend on details we can't yet pin down. These elements are the seeds of planets, of life, and their origins tie us to the stars in a quiet cosmic embrace. Scientists observe supernovae with telescopes, from ground-based observatories to space-based instruments like the Hubble and James Webb Space Telescopes. They study the light, the spectra, to learn about the explosion's chemistry and physics. But each observation raises new questions. Why do some supernovae have unusual light curves, fading faster or slower than expected? What role do magnetic fields play in the explosion? The answers lie in the stars themselves, waiting to be discovered. The mystery of why stars explode is also a story of connection. Every atom in your body, heavier than helium was, forged in a star, many in the fiery hearts of supernovae. When you look at the night sky, you're seeing the descendants of those explosions, the remnants of stars that gave everything to the universe. It's a comforting thought, a reminder that we're part of the cosmos, woven from its light, its energy, its endings. Why do stars explode? They explode because their cores can no longer resist gravity, because fusion falters, because the universe demands creation from destruction. But the details Why some explode brightly, why others collapse silently, how the explosion unfolds, remain a gentle enigma, a question that invites us to wonder, to dream. Scientists will keep searching, studying the light of distant stars, piecing together the story of their final moments. As we leave this mystery, let your thoughts soften like starlight fading into the night. Supernovae remind us that endings can be beautiful, that light can emerge from chaos, that we are all made of stars. Rest now and imagine those cosmic fireworks blazing across the universe, guiding you towards sleep. Another mystery awaits, but for now, just drift. Imagine a distant moon, orbiting the mighty planet Jupiter, its surface gleaming like a frozen pearl in the cosmic night. This is Europa, a world covered in ice, smooth and cracked, reflecting the faint light of the stars. But beneath this icy shell lies a secret, a vast ocean of liquid water, hidden in darkness, stretching across the moon. Could this ocean harbor life, alien creatures swimming in its depths? What lies beneath Europa's ice? Let's drift into this gentle mystery floating through the cosmos, letting the quiet wonder of this distant world guide us towards sleep. Close your eyes and picture Europa, a small moon, yet grand in its mystery, circling Jupiter in a silent, graceful dance. Its surface is a mosaic of ice, crisscrossed with reddish cracks, like veins in a frozen heart. These cracks hint at something alive beneath, a hidden world where water flows, perhaps as deep as Earth's oceans combine. This subsurface ocean, kept warm by forces beyond the sun's reach, is one of the most tantalizing places in our solar system. A place where life might thrive, far from the warmth of a star. Why does this matter? Europa's ocean could be a cradle for life, a chance to find alien organisms in our own cosmic backyard. Water is the key to life as we know it, and Europa's ocean might hold the ingredients, chemicals, energy, and time for something to emerge. Perhaps microbes, perhaps more. The question of what lies beneath its ice is a whisper from the universe, asking us to imagine life beyond Earth, to dream of worlds unseen, a story as comforting as it is profound. Let's linger in this thought, floating above Europa's icy plains, gazing at its frozen beauty, sensing the ocean below. It's a soothing idea, isn't it? That beneath this cold, distant moon, a hidden sea might pulse with life, a quiet reminder that the universe is full of possibilities waiting to be explored. Europa is a beacon of hope, a place where the search for life feels close, tangible, like a star you can almost touch. Now let's explore the science, softly, like tracing a story across the night sky. Scientists first suspected Europa's ocean in the 1970s when the Voyager spacecraft flew past, capturing images of its smooth, cracked surface. These cracks, called lineae, suggested a dynamic world, where ice shifts and flexes. Later, the Galileo spacecraft, orbiting Jupiter in the 1990s, confirmed the ocean's existence. It detected a magnetic field around Europa, induced by Jupiter's powerful magnetism, a sign of a conductive layer beneath the ice, likely a salty, liquid ocean. Imagine that ocean, vast and deep, perhaps 100 miles thick, dwarfing Earth's seas. The ice above it is thick, maybe 10 to 15 miles, a frozen shield protecting the water below. But this ocean isn't cold and lifeless. It's warmed by Jupiter's tidal forces. As Europa orbits, Jupiter's gravity tugs and squeezes the moon, generating heat through friction, much like kneading dough. This tidal heating keeps the ocean liquid, creating a world where water, the elixir of life, flows freely in eternal darkness. What could live in such a place? That's where the mystery deepens, like a dream you can't quite grasp. On Earth, life thrives in extreme environments, deep sea vents, Antarctic ice, acidic springs fueled by chemical energy. Europa's ocean might have similar conditions. Scientists believe hydrothermal vents like those on Earth's ocean floor could exist on Europa's seabed, spewing minerals and heat. These vents could support ecosystems, with microbes feeding on chemical reactions, forming the base of a food chain we can only imagine. Picture tiny organisms glowing faintly in the dark, clustering around warm vents, living in a world without sunlight. Or perhaps something larger, stranger, adapted to the ocean's pressures and chemistry. The possibilities are endless, yet grounded in science. Europa's ocean likely contains salts, organic compounds, and energy sources, all ingredients for life. But does life exist there? We don't know, and that's what makes this question so beautiful. A puzzle floating in the cosmic sea. The evidence for the ocean is strong, but its secrets remain hidden. Galileo's measurements showed water vapor plumes, geysers erupting through cracks in the ice, spraying ocean material into space. These plumes suggest the ocean is active, interacting with the surface, perhaps even accessible. The Hubble Space Telescope has spotted hints of these plumes, and scientists hoped they could contain traces of life, like organic molecules, microbial fragments, waiting to be studied. The ice is a barrier, a challenge we're only beginning to overcome. Scientists are planning missions, like NASA's Europa Clipper, set to launch in the 2020s, to explore this moon in detail. The Clipper will orbit Jupiter, making close flybys of Europa, using radar to peer beneath the ice, analyzing plumes for chemical clues. It won't land, but it will bring us closer to understanding what lies below, mapping the ocean's depth, its salinity, its potential for life. What would life on Europa look like? That's another layer of the mystery, soft and intriguing. If microbes exist, they might resemble Earth's extremophiles, simple but resilient, thriving on chemical energy. If more complex life exists, it could be utterly alien, shaped by an environment we can't fully imagine. The ocean's darkness, its pressure, its chemistry, all would sculpt life in unique ways, creating organisms that might defy our expectations, like creatures from a cosmic dream. The mystery also asks how life could have started. On Earth, life emerged in water, perhaps near hydrothermal vents, fueled by chemical reactions. Europa's vents could offer a similar cradle, but the process is uncertain. Did life arise independently, sparked by the moon's unique conditions? Or could it share a common origin with Earth, carried by comets or meteorites in a process called panspermia? The question drifts like a whisper, connecting Europa to the broader story of life in the universe. Scientists are also curious about the ocean's chemistry. Is it rich in organic compounds, the building blocks of life? Does it have the right balance of energy and nutrients? The plumes offer a chance to find out, as they might carry samples of the ocean's contents. Future missions could fly through these plumes, collecting particles, analyzing them for signs of life. It's a tantalizing possibility, a chance to touch Europa's secrets without piercing its icy shell. The challenge of exploring Europa adds to the mystery's allure. The ice is thick, and landing a probe to drill through it is a distant dream, requiring technology we don't yet have. Radiation from Jupiter's magnetic field batters Europa's surface, making exploration risky. Yet scientists dream of submarines, robotic explorers that could swim the ocean's depths, searching for vents, for life, for answers. These dreams are part of the story, a quiet pursuit that connects us to the cosmos, what lies beneath Europa's ice. It's an ocean, vast and hidden, possibly teeming with life, possibly silent. The truth lies beyond our reach, waiting for missions like the Europa Clipper to bring us closer. For now, the question is enough, a gentle enigma that invites us to imagine, to feel the pull of a distant world, to rest in its mystery. It's a story of possibility, of water and life, of a moon that might hold secrets as deep as the universe itself. The beauty of this mystery lies in its hope, its promise of discovery. We know Europa's ocean exists, that it's a place where life could thrive, but we don't know what's there. This balance of knowledge and wonder is soothing, a reminder that the universe is full of surprises waiting to be explored. As we ponder this question, we're not just seeking answers. We're dreaming of new worlds, feeling the pulse of the cosmos. Think of Europa now, orbiting silently, its icy surface hiding a sea of possibilities. It's a reminder that life might be closer than we think, that the universe is alive with potential, even in its coldest corners. As you listen, let this thought comfort you. Let it carry you toward rest, like a moon drifting in a cosmic tide. What lies beneath Europa's ice? It's a question that connects us to the search for life, to the mysteries of water and warmth in a frozen world. As we leave this mystery behind, let your thoughts soften, like ice melting into water. Europa's ocean waits, hidden and serene, guiding you towards sleep. Another mystery awaits, but for now, just drift. Imagine the universe as a vast, quiet sea, dotted with stars and galaxies, each glowing softly in the cosmic night. Then suddenly a flash of light erupts, brighter than a billion. Suns piercing the darkness for just a moment before fading away. This is a gamma ray burst, a fleeting explosion of energy, one of the most powerful events in the cosmos. Where do these bursts come from? What causes them to blaze so fiercely? Let's drift into this gentle mystery, floating through the stars, letting their distant lights guide us towards sleep. Close your eyes and picture a distant galaxy, billions of light years away, where something extraordinary is happening. In an instant, a burst of gamma rays, the most energetic form of light, floods the universe, outshining everything around it. These bursts last only seconds or minutes, yet their energy is unimaginable, carrying the power of countless stars in a single flash. They're like cosmic fireworks, brief but dazzling, leaving astronomers to wonder about their origins, their purpose, their secrets. Why does this matter? Gamma-ray bursts are windows into the universe's most extreme moments of creation and destruction that shape the cosmos. They tell us about the lives and deaths of stars, the collisions of exotic objects, and the forces that govern the universe's evolution. Asking what causes them is like asking how the universe writes its most dramatic stories, a question that feels both vast and intimate, a lullaby whispered by the stars. Let's linger in this thought, floating in the glow of a gamma-ray burst, feeling its fleeting warmth across the vastness of space. It's a comforting idea, isn't it, that even in the deepest reaches of the cosmos, moments of brilliance can emerge, lighting up the darkness, connecting us to the universe's grandest events. Gamma-ray bursts are a reminder that the universe is alive, dynamic, full of surprises waiting to be explored. Now let's explore the science softly, like tracing a story across the night sky. Gamma-ray bursts were first discovered in the 1960s by accident, when satellites designed to detect nuclear tests picked up strange signals from space. These flashes of gamma rays, invisible to the human eye, were coming from far beyond our galaxy, carrying energies that defied explanation. At first, scientists were puzzled, unsure if they were nearby events or cosmic phenomena. Over decades, they pieced together a story of extraordinary power. There are two main types of gamma-ray bursts, each with its own tale. Long bursts, lasting more than a couple of seconds, are thought to come from the deaths of massive stars. Imagine a star many times larger than our sun, burning through its fuel over millions of years. When its core can no longer sustain fusion, it collapses under gravity, forming a black hole or neutron star. This collapse triggers a supernova, a massive explosion, and in some cases a gamma-ray burst, as jets of energy blast out at nearly the speed of light. Picture that moment, the star's core imploding, its outer layers erupting, and twin beams of gamma rays shooting through space like lighthouses in the cosmic dark. These jets are incredibly focused, so we only see the burst if one point directly at Earth. The energy is staggering, releasing in seconds what our sun emits over billions of years. It's a dramatic end, a star's final act, scattering light and elements across the universe. Short bursts, lasting less than 2 seconds, tell a different story. These are believed to come from the collisions of neutron stars, the dense remnants of dead stars, or a neutron star merging with a black hole. Imagine 2 neutron stars, each heavier than the sun but smaller than a city, spiraling toward each other, drawn by gravity's relentless pull. When they collide, they release a burst of gamma rays, followed by a glow of heavy elements, like gold and silver, forged in the chaos. What causes these bursts to shine so brightly? That's where the mystery deepens, like a dream you can't quite hold. For long bursts, scientists think the jets form as material, spirals into the newly formed black hole, heating up and accelerating to incredible speeds. But the details, how the jets stay so focused, how they convert energy into gamma rays, are still unclear. Computer simulations struggle to capture the physics, and each burst seems to have its own quirks, defying simple explanations. Short bursts are equally enigmatic. The merger of neutron stars produces a burst of energy, but why? Are some brighter or shorter than others? In 2017, astronomers witnessed a neutron star collision detected by both gamma rays and gravitational waves, a historic event that confirmed the link. Yet not all short bursts fit this model. Some might involve other processes like magnetars, neutron stars with intense magnetic fields, or even unknown phenomena, adding layers to the mystery. The energy of gamma ray bursts is another puzzle. They are so powerful that if one occurred nearby, it could disrupt Earth's atmosphere. Though the odds are vanishingly small, most bursts come from distant galaxies, their light traveling billions of years to reach us, carrying stories of the early universe. But what determines their intensity? Why do some bursts outshine others? Scientists study their afterglows, the fading light in X-rays and visible wavelengths, to learn more, but the answers remain elusive. Gamma ray bursts also play a role in the universe's evolution, shaping its history in ways we don't fully understand. Long bursts tied to massive stars were more common. In the early universe, when star formation was at its peak, they marked the deaths of the first stars, helping us trace cosmic history. Short bursts from neutron star mergers produce heavy elements, enriching galaxies over time. But how many bursts occurred? How did they influence galaxy formation? These questions linger, soft and intriguing. Scientists observe gamma ray bursts with specialized telescopes like NASA's Swift and Fermi satellites, designed to catch their fleeting light. When a burst is detected, observatories worldwide turn to study its afterglow, analyzing its spectrum to learn about the explosion's environment. Each burst is a snapshot, a glimpse into a violent moment, but the data raises new questions. Why do some bursts have unusual light patterns? What causes dark bursts with little visible afterglow? The cosmos keeps its secrets, inviting us to wonder. The mystery of gamma ray bursts is also a story of connection. The elements forged in these bursts, gold in your jewelry, silver in your coins, link us to the universe's most extreme events. When you look at the night sky, you're seeing a universe shaped by bursts, their energy woven into the fabric of galaxies. It's a comforting thought, a reminder that we're part of the cosmos, born from its light, its chaos, its brilliance. Could gamma ray bursts hold other surprises? Some scientists speculate about rare types caused by exotic events like quark stars or cosmic strings, hypothetical structures from the early universe. Others wonder if bursts could carry signals, though there's no evidence for this. These ideas, while speculative, add to the mystery's allure, suggesting the universe has more stories to tell, waiting to be discovered. What are gamma ray bursts? They're the universe's most powerful explosions, born from the deaths of massive stars, or the collisions of neutron stars, lighting up the cosmos with unimaginable energy. But their triggers, their variations, their full impact, these remain gentle enigmas, questions that invite us to dream, to float in the vastness of the universe. Scientists will keep searching, chasing the light of distant bursts, piecing together their stories across billions of years. As we leave this mystery, let your thoughts soften like starlight fading into the night. Gamma-ray bursts remind us that the universe is dynamic, that moments of brilliance can emerge from chaos, that we are all connected to its grandest events. Rest now and imagine those cosmic flashes blazing across the universe, guiding you towards sleep. Another mystery awaits, but for now, just drift. Imagine the universe, vast and boundless, stretching beyond the stars, beyond the galaxies, into an infinity you can scarcely grasp. Picture it not just as a collection of light and matter, but as a shape, a form that defines its very existence. Is it flat, like an endless sheet of starlight, curved, like a cosmic sphere, or something stranger, folding in ways we can't imagine? This is the mystery of the universe's geometry. What shape does our cosmos hold? How does it define our place within it? Let's drift into this gentle enigma, floating through the stars, letting their quiet glow guide us towards sleep. Close your eyes and envision the universe as a canvas painted with galaxies, nebulae, and the soft glow of ancient light. This canvas isn't just a backdrop. It has a structure, a geometry that governs how light travels, how gravity pulls, how the cosmos evolves. The shape of the universe could determine its fate, whether it expands forever, collapses back on itself, or balances in between. It's a question that feels both grand and intimate, like tracing the outline of a dream, asking where we fit in the cosmic design. Why does this matter? The universe's geometry is a key to understanding its past and future, a clue to the forces that shaped it from the Big Bang to now. It connects us to the cosmos in a profound way, suggesting that the shape of reality itself influences every star, every planet, every moment of our lives. Asking what form the universe takes is like asking what kind of story we're living in. A soothing mystery that invites us to wonder, to rest in its vastness. Let's linger in this thought, floating in the expanse of the cosmos, feeling its shape around you, like a blanket of stars. It's a comforting idea, isn't it, that the universe has a form, a structure, even if we can't fully see it, guiding the paths of light and matter, holding us in its embrace. The geometry of the cosmos is a reminder that we're part of something greater, a pattern woven across billions of years, waiting to be understood. Now let's explore the science gently, like whispering a tale under the night sky. The geometry of the universe is tied to its density, the amount of matter and energy it contains. Scientists describe three possible shapes: flat, open, or closed. A flat universe is like an infinite plane, where parallel lines never meet, and the angles of a triangle add up to exactly 180 degrees. An open universe curves outward like a saddle, stretching forever. A closed universe curves inward, like a sphere looping back on itself, finite but without edges. Imagine drawing a triangle across the cosmos, its lines made of starlight. In a flat universe, that triangle behaves as you'd expect, its angles perfectly balanced. In an open universe, the angles shrink, as if the cosmos is pulling them apart. In a closed universe, the angles grow, as if the universe is folding them together. This geometry isn't just a mathematical idea. It shapes how the universe expands, how galaxies form, how time itself unfolds. Scientists study the universe's geometry by looking at its oldest light, the cosmic microwave background, or CMB, a snapshot of the cosmos when it was just 380,000 years old. A CMB is like a cosmic tapestry filled with tiny temperature variations, ripples from the Big Bang. By measuring these ripples, scientists can infer the universe's shape. In a flat universe, the ripples have a specific size. In an open or closed universe, they appear distorted, stretched or compressed by the cosmos's curvature. Picture that. Ancient light, traveling for billions of years, carrying secrets of the universe's birth. In the early 2000s, the Wilkinson microwave anisotropy probe, or WMAP, mapped the CMB with unprecedented detail, followed by the Planck satellite. Their measurements suggest the universe is remarkably flat, its geometry balanced to within a fraction of a percent. It's as if the cosmos is a perfectly stretched canvas, infinite and even, a discovery that feels both elegant and mysterious. But why is the universe flat? That's where the mystery deepens. Like a dream you can't quite hold. A flat universe requires a precise balance of matter, energy, and expansion. A cosmic coincidence that puzzles scientists. Too much matter and the universe would be closed, collapsing under gravity. Too little and it would be open, expanding too fast for galaxies to form. The flatness suggests a fine-tuned cosmos. But what set this balance? Was it chance? Or something deeper? One clue comes from cosmic inflation, a rapid expansion in the universe's first moments. Inflation stretched the cosmos, smoothing out any curvature, making it appear flat, like a balloon blown up so large its surface seemed even. This theory explains the flatness, but it raises new questions. Did inflation happen everywhere? Could other parts of the universe have different geometries hidden beyond our view? The answers drift like whispers, inviting us to imagine. The mystery also touches on the universe's fate. In a flat universe, expansion continues forever, slowing but never stopping, as dark energy pushes galaxies apart. In a closed universe, gravity might eventually win, pulling the cosmos back into a big crunch. An open universe would expand endlessly, growing cold and sparse. The flat geometry we observe suggests a universe that will drift apart, but small uncertainties remain, leaving room for wonder. Could the universe have a more complex shape? Some scientists propose exotic geometries like a torus, a cosmic donut where space loops back on itself. Imagine traveling in a straight line and returning to your starting point, as if the universe is a finite maze without boundaries. These ideas are speculative, hard to test, but they add a layer of intrigue, suggesting the cosmos might be stranger than we think. A puzzle woven into its very fabric. Scientists are still probing the universe's geometry, using new telescopes and at experiments to refine their measurements. The Simons Observatory and future missions like Lightbird will study the CMB with even greater precision, searching for hints of curvature or unusual patterns. They're also looking at the distribution of galaxies, the cosmic web, to see if it aligns with a flat universe. Each observation brings us closer, but the full picture remains elusive, a gentle enigma waiting to be solved. The mystery of the universe's geometry is also a story of connection. The shape of the cosmos influences every light ray that reaches your eyes, every gravitational pull that holds the stars. When you look at the night sky, you're seeing a universe shaped by its geometry, a form that links you to the Big Bang, to the first moments of creation. It's a comforting thought, a reminder that we're part of a grand design, even if we don't fully understand it. What is the universe's geometry? It's likely flat, an infinite canvas stretched by inflation, guiding the paths of light and matter. But why it's flat, whether it could be different elsewhere, or if it hides a more complex shape? These are questions that linger, soft and intriguing, inviting us to dream, to float in the cosmos's embrace. Scientists will keep searching, mapping the CMB, tracing the cosmic web, seeking the shape of reality itself. As we leave this mystery, let your thoughts soften, like starlight fading into the night. The universe's geometry reminds us that we're part of a vast, elegant cosmos, a structure that holds us gently, guiding our place in the stars. Rest now and imagine that cosmic canvas, stretching forever, guiding you towards sleep. Another mystery awaits, but for now, just to drift. Imagine the universe as a vast, shimmering tapestry, woven with stars, galaxies, and the soft glow of ancient light. Every thread in this tapestry is made of matter, the stuff of planets, of life, of you and me. But somewhere in this cosmic weave, a piece is missing. Half of the ordinary matter, the baryons that should fill the universe, is nowhere to be found. Where are these missing baryons? Why can't we see them? Let's drift into this gentle mystery floating through the cosmos, letting the quiet pull of the stars guide us towards sleep. Close your eyes and picture the universe in its earliest moments, just after the Big Bang, a hot, dense sea of particles. Among these particles are baryons, protons and neutrons, the building blocks of atoms, of everything tangible. Scientists know how. Many baryons should exist, a number calculated from the universe's first light. Yet, when they look at the cosmos today, counting the matter in stars, planets, and gas, clouds, they find only half of what should be there. The rest is hidden, a cosmic riddle, waiting to be solved. Why does this matter? Baryons are the ordinary matter that makes up our world, the substance of our bodies, our earth, our skies. Finding the missing baryons would complete our picture of the universe, revealing how matter flows, how galaxies form, how the cosmos holds itself together. Asking where they are is like searching for a lost thread in the universe's story, a soothing mystery that connects us to the very stuff of existence. A question as comforting as it is profound. Let's linger in this thought, floating among the galaxies, feeling the presence of matter all around you, even the parts we can't see. It's a calming idea, isn't it? That the universe is full of hidden treasures, pieces of itself waiting to be found, weaving us into its grand design. The missing baryons are a reminder that the cosmos is vast, mysterious, and alive with secrets, holding us gently in its embrace. Now, let's explore the science, softly like whispering a tale under the starlit sky. Baryons are the ordinary matter of the universe, distinct from dark matter and dark energy, which make up most of the cosmos, but remain elusive. Scientists calculate the total amount of baryons using the cosmic microwave background, or CMB, the faint glow of the Big Bang's aftermath. The CMB tells the universe's composition in its infancy, showing that baryons should account for about 5% of its total energy, a precise figure etched in ancient light. Imagine that early universe, a soup of particles cooling as it expands, baryons forming the seeds of stars and galaxies. By studying the CMB, scientists can predict how many baryons should exist today, scattered across the cosmos. They also use the abundance of light elements like hydrogen and helium, formed in the Big Bang's first minutes, to confirm this number. These measurements agree, painting a clear picture of the universe's baryonic budget, a cosmic inventory of ordinary matter. But when scientists look at the modern universe, they find a problem. They count the baryons in stars, planets, and interstellar gas, using telescopes to measure the light and mass of galaxies. They study hot gas in galaxy clusters, glowing in X-rays, and cold gas clouds, absorbing starlight. Yet all these sources together account for only about half the expected baryons. The other half, the missing baryons, are nowhere to be seen, as if they have slipped through the universe's fingers. Where could they be? That's where the mystery deepens, like a dream you can't quite grasp. One leading theory suggests that missing baryons are hiding in the cosmic web, a vast network of filaments, walls, and voids that connects galaxies across the universe. Picture a spider web stretching through space, its threads made of gas, too faint and diffuse to detect easily. These filaments, warmed to millions of degrees, could hold the missing baryons, scattered in a form that's nearly invisible to our telescopes. Imagine those filaments glowing softly, threading galaxies together like pearls on a cosmic string. They're made of gas, mostly hydrogen, heated by gravity and shock, waves as the universe evolved. This gas, known as the warm, hot intergalactic medium, or WIM, is thought to contain the missing baryons, spread so thinly that it emits little light. Detecting it is like searching for a whisper in a storm, a challenge that makes the mystery all the more intriguing. Scientists have found clues supporting this idea. In recent years, X-ray telescopes like XMM Newton and Chandra have detected faint signals from hot gas in the cosmic web, bridging distant galaxies. These signals suggest the missing baryons are there, locked in. Filaments, their warmth betraying their presence. Studies of the Sunyaev-Zeldovich effect, where CMB light scatters off hot gas, have also hinted at baryons in these structures, offering hope that the puzzle is nearing a solution. But the cosmic web isn't the whole story. Some baryons might be hiding in other forms, like cold gas clouds too faint to see, or in galaxies too dim to detect. Others could be locked in exotic states, like plasma around black holes or scattered by galactic winds, blown out of galaxies by star formation. Each possibility adds a layer to the mystery, suggesting the universe is more complex, more dynamic than we thought. A tapestry with hidden threads. Why haven't we found all the baryons? That's another question, soft and intriguing. Our telescopes are powerful, but they struggle to see faint, diffuse gas across vast distances. The cosmic web's filaments are spread thin, their light drowned out by brighter sources. Detecting them requires precise measurements, often at the edge of our technology's limits. Scientists are developing new tools like the Athena X-ray observatory and the Square Kilometer Array to probe these hidden regions, hoping to map the missing baryons in detail. The mystery also raises deeper questions about the universe's evolution. Baryons aren't just static. They flow, moving through galaxies, filaments, and voids, driven by gravity and cosmic forces. Understanding where they are would reveal how galaxies formed, how matter clumped together, how the cosmic web grew. If the missing baryons are in the web, they might hold clues to the universe's structure, its history, its future, connecting us to the cosmos's grand narrative. Could our calculations be wrong? Some scientists wonder if the missing baryons point to flaws in our models. Perhaps the CMB or element abundances are misread, or maybe baryons behave differently than we expect, interacting with dark matter in unknown ways. These ideas are speculative, but they add to the mystery's allure, suggesting the universe might surprise us, revealing new physics, new truths, hidden in its ordinary matter. The search for the missing baryons is a story of connection. Every atom in your body is a baryon, forged in the Big Bang, shaped by the universe's evolution. When you look at the night sky, you're seeing a cosmos made of the same stuff, some of it hidden, waiting to be found. It's a comforting thought, a reminder that we are part of the universe's tapestry, woven from its matter, its mysteries, its light. Where are the missing baryons? They're likely in the cosmic web, in faint filaments threading the universe, or scattered in forms we can't yet see. But their exact hiding places, their full story, these remain gentle enigmas, questions that invite us to dream, to float in the cosmos's embrace. Scientists will keep searching, mapping the web, chasing faint signals, seeking the matter that binds us all. As we leave this mystery, let your thoughts soften, like starlight fading into the night. The missing baryons remind us that the universe is full of hidden treasures, that even its ordinary matter holds secrets. Rest now and imagine those cosmic filaments glowing softly, guiding you towards sleep. Another mystery awaits, but for now, just drift. Imagine the vastness of space, a quiet sea of stars stretching beyond the horizon of your dreams. Suddenly, a strange visitor appears, gliding through our solar system, unlike anything we've seen before. It's long, cigar-shaped, tumbling through the void, catching the sun's faint light as it speeds by. This is Oumuamua, the first interstellar object ever observed passing through our cosmic neighborhood. But what was it? A comet? An asteroid? Or something stranger? Let's drift into this gentle mystery floating among the stars. letting the quiet pull of this enigmatic traveler guide us towards sleep. Close your eyes and picture Oumuamua, a dark reddish object, roughly 800 meters, long spinning end over end as it journeys through our solar system. Discovered in 2017 by a telescope in Hawaii, its name means scout or messenger in Hawaiian, a fitting title for a visitor from beyond. It moved too fast to be bound by the sun's gravity, tracing a path that told astronomers it came from another star, a wanderer from the depths of interstellar space, passing through before vanishing into the cosmic night. Why does this matter? Oumuamua is a glimpse of the universe beyond our solar system, a piece of another star's story carried to us across unimaginable distances. Its strange shape, its unexpected behavior spark questions about the nature of interstellar objects and our place in the cosmos. Asking what Oumuamua was is like listening to a whisper from another world, a soothing mystery that connects us to the vast, unknown reaches of space. A story as comforting as it is profound. Let's linger in this thought, floating alongside Oumuamua, watching it tumble through the darkness, its surface glinting faintly under starlight. It's a calming idea, isn't it? That the universe sends us visitors, silent travelers bearing secrets from distant stars, reminding us that we're part of a grand and interconnected cosmos. Oumuamua is a beacon of wonder, a mystery that invites us to imagine, to rest in the beauty of the unknown. Now, let's explore the science, softly, like tracing a story across the night sky. Oumuamua was spotted by the Pan-STARRS telescope on October 19th, 2017, already on its way out of the solar system, moving at over 50 kilometers per second. Its trajectory was hyperbolic, meaning it wasn't orbiting the sun but passing through. A clear sign it originated elsewhere. Astronomers calculated it came from the direction of the constellation Lyra, perhaps ejected from a star system billions of years ago. Wandering the galaxy until it crossed our path to imagine that journey. Oumuamua drifting through the Milky Way, untouched by any star's gravity, a solitary traveler in the cosmic void. Its shape was unlike anything in our solar system, elongated and flat, possibly disc-like or cigar-shaped, with no clear comparison to comets or asteroids. Its surface was reddish, likely from cosmic rays bombarding it over eons, giving it a hue similar to some distant Kuiper Belt objects. This strange appearance puzzled scientists, setting Oumuamua apart as a cosmic oddity. What was it made of? That's where the mystery deepens, like a dream you can't quite hold. At first, astronomers thought Oumuamua might be a comet, a chunk of ice and dust that outgasses when heated by a star, creating a glowing coma or tail. But Oumuamua showed no such activity, no dust, no gas, even as it passed close to the sun. This led some to classify it as an asteroid, a rocky fragment, but its shape and behavior didn't quite fit. The lack of outgassing made it hard to pin down, leaving its composition a tantalizing question. Then came another surprise, Oumuamua's speed. As it moved away from the sun, it accelerated slightly, more than gravity alone could explain. This non-gravitational boost suggested something was pushing it, but without a visible coma, traditional comet outgassing seemed unlikely. Scientists proposed it might be a hydrogen iceberg, with frozen hydrogen sublimating into gas, providing a subtle thrust. Others suggested it could be a loosely bound object, fragmenting under solar heat, ejecting material to propel itself. Each idea adds a layer to the mystery, a whisper from the cosmos. The most provocative theory came from astronomer Avi Loeb, who suggested Oumuamua might be artificial, perhaps a light sail or probe from an alien civilization. Picture a thin reflective sail, catching starlight to drift through space, built by beings we can't imagine. Its shape, acceleration, and lack of outgassing fit this idea, though it's highly speculative, with no direct evidence. Most scientists favor natural explanations, but the possibility lingers, a dreamy notion that sparks the imagination, inviting us to wonder about life beyond our stars. Why was Oumuamua so strange? That's another question, soft and intriguing. Its elongated shape is rare, even among asteroids or comets in our solar system. Simulations suggest interstellar objects might form differently, shaped by their parent star's environment or eons of cosmic radiation. But we've only seen one such object, making it hard to generalize. Oumuamua's tumbling, motion spinning chaotically, suggests a violent past, perhaps a collision or ejection from its home system, but the details remain elusive. Could there be more like it? Scientists now know interstellar objects are common, with estimates suggesting several pass through our solar system each year. Oumuamua was the first we detected, followed by a second, Borisov, in 2019, which behaved like a typical comet. Future telescopes like the Vera C. Rubin Observatory will hunt for more, hoping to catch these visitors early, study their compositions, and compare them to Oumuamua. Each new discovery could shed light on this mystery, revealing whether Oumuamua was unique or one of many. The challenge of studying Oumuamua adds to its allure. By the time we spotted it, it was already leaving too far for detailed observations. Telescopes tracked its light, its motion, but couldn't resolve its surface or send a probe to catch up. Its brief visit left us with more questions than answers, a fleeting glimpse of the interstellar unknown. Scientists dream of future missions, spacecraft designed to intercept such objects, but for now, Oumuamua's secrets are carried away into the cosmic night. What was Oumuamua's origin? It might have come from a young star system where planets were still forming, ejecting debris into space. Or perhaps it was a fragment of a dead star, torn apart by gravity. Its path suggests it wandered for billions of years, a silent traveler with no home. The uncertainty is part of the mystery's charm, a reminder that the universe is full of stories we've yet to hear, waiting to be explored. The mystery of Oumuamua is also a story of connection. It reminds us that our solar system is not an island, but part of a vast galactic community where objects drift between stars, carrying pieces of their origins. When you look at the night sky, you're seeing a universe alive with motion, with visitors like Oumuamua linking us to distant worlds. It's a comforting thought, a reminder that we are part of the cosmos, woven from its wanderers, its light. What was Oumuamua? It was an interstellar object, perhaps a comet, an asteroid, or something stranger, a messenger from another star. But its shape, its acceleration, its true nature, these remain gentle enigmas, questions that invite us to dream, to float in the cosmos's embrace. Scientists will keep searching, watching for the next visitor, hoping to unravel the secrets Oumuamua left behind. As we leave this mystery, let your thoughts soften, like starlight fading into the night. Oumuamua reminds us that the universe is full of surprises, that even a single object can spark wonder, connecting us to the stars. Rest now, and imagine that cosmic traveler gliding through the void, guiding you towards sleep. Another mystery awaits, but for now, just drift. Imagine a distant moon, orbiting the ringed giant Saturn, its surface shrouded in a golden haze, glowing softly in the cosmic night. This is Titan, a world unlike any other, where lakes shimmer with liquid methane, rivers carve valleys, and rain falls from an alien sky. Beneath its icy crust, an ocean of water might flow, hidden in darkness. Could life exist on Titan, thriving in its strange cold chemistry? What kind of creatures might call this moon home? Let's drift into this gentle mystery, floating through the stars, letting the quiet allure of Titan guide us towards sleep. Close your eyes and picture Titan larger than the planet Mercury, wrapped in a thick orange atmosphere denser than Earth's. Its surface is a frozen landscape, dotted with lakes, rivers, and seas, not of water, but of methane and ethane, liquids that flow in the moon's frigid cold, where temperatures hover near minus 290 degrees Fahrenheit. Yet, beneath this icy exterior, scientists suspect a global ocean of liquid water warmed by the moon's core, a hidden sea that whispers of life's possibilities. Why does this matter? Titan is a laboratory for life's potential, a place where chemistry mimics Earth's in eerie ways, but with a twist. Its methane-based lakes and water-based ocean offer two paths for life, one familiar, one alien, challenging our ideas of where life can thrive. Asking if life exists on Titan is like dreaming of new worlds, a soothing mystery that connects us to the cosmos, a story as comforting as it is profound. Let's linger in this thought, floating above Titan's hazy skies, gazing at its methane lakes, glinting under Saturn's glow. It's a calming idea, isn't it? That this distant moon, so different from Earth, might harbor life, creatures adapted to its strange beauty, reminding us that the universe is full of surprises, waiting to be explored. Titan is a beacon of wonder, a place where life's story might be written in ways we can't yet imagine. Now, let's explore the science, softly, like tracing a story across the night sky. Titan's mysteries were unveiled by the Cassini spacecraft, which orbited Saturn from 2004 to 2017, sending back images of a world both alien and familiar. Its radar revealed lakes and rivers, while the Huygens probe landing on Titan in 2005 showed a surface of ice and organic-rich pebbles, bathed in a dim orange light. These discoveries painted Titan as a moon with Earth-like processes, rain, erosion, seasons, but driven by methane instead of water. Imagine standing on Titan's shore, watching methane rain fall gently, pooling into lakes that reflect the hazy sky. This methane cycle, like Earth's water cycle, creates a dynamic world where organic molecules, carbon-based compounds essential for life, rain down from the atmosphere. Titan's air is rich in nitrogen and methane, and ultraviolet, light from the sun, breaks these molecules apart, forming complex organics that drift to the surface, building a chemistry that feels tantalizingly close to life's beginnings. Could life exist in Titan's lakes? That's where the mystery deepens, like a dream you can't quite grasp. On Earth, life depends on liquid water, but Titan's surface is too cold for that. Instead, its methane lakes might host exotic life, using methane as a solvent, the way Earth's life uses water. Scientists imagine microbes or even larger organisms with membranes and metabolisms adapted to liquid methane, feeding on organic molecules or hydrogen. Such life would be utterly alien, a chemistry we can only speculate about. Picture tiny creatures, perhaps glowing faintly, drifting in Titan's lakes, metabolizing in ways we don't understand. Laboratory experiments on Earth have simulated Titan's conditions, showing that organic molecules can form complex structures like azotosomes, which might act as cell membranes in methane. These findings suggest life is possible, but we don't know if Titan's chemistry has crossed the threshold from complex molecules to living organisms. A question that lingers like a whisper from the cosmos. Beneath Titan's surface lies another possibility, a subsurface ocean of liquid water, similar to those on Europa or Enceladus. Cassini's measurements of Titan's gravity and shape suggest this ocean, perhaps 50 miles deep, lies beneath 60 miles of ice. This water, kept liquid by tidal heating from Saturn's gravity, could be rich in salts and ammonia, creating a habitable environment like Earth's deep oceans. If hydrothermal vents exist on the ocean floor, they might support life, microbes thriving on chemical energy, much like those in Earth's seas. Imagine that hidden ocean, warm and dark, teeming with simple life forms, clinging to vents or floating in currents. This water-based life would be more familiar, resembling Earth's microbes, but adapted to Titan's unique conditions. The ocean's isolation beneath thick ice makes it hard to study, but its presence offers a second chance for life, a dual mystery of surface and subsurface, methane and water, alien and familiar. What would Titan's life need to survive? That's another layer of the mystery, soft and intriguing. In the lakes, life would require a metabolism that works in extreme cold, using methane or ethane as a medium. In the ocean, life would need energy, perhaps from chemical reactions between water and minerals, or from organic molecules seeping through the ice. Titan's surface is bathed in organic material, and if this reaches the ocean, it could fuel a rich ecosystem, a possibility that sparks the imagination. The challenge of finding life on Titan adds to the mystery's allure. Cassini gave us a glimpse, but it couldn't search for life directly. Future missions like NASA's Dragonfly, a drone set to explore Titan in the 2030s, will study its chemistry flying across its surface, sampling lakes and dunes. Dragonfly will look for biosignatures, chemical signs of life, but it won't reach the subsurface ocean, leaving that mystery for future explorers, perhaps submarines or drills that could pierce the ice. Could life have started on Titan? The moon's organic wealth suggests it's possible. On Earth, life emerged in water, perhaps near vents, fueled by chemistry. Titan's lakes and ocean could offer similar cradles, but the process is uncertain. Did life arise independently, sparked by Titan's unique environment? Or could it share a common origin with Earth, carried by comets in a process called panspermia? The question drifts like a haze, connecting Titan to the broader story of life in the universe. Titan's atmosphere adds another dimension. Its organic molecules, formed by solar radiation, create a smog that shields the surface, preserving its chemistry. This stability might help life persist, but the cold slows reactions, making the leap to life harder than on Earth. Scientists debate whether Titan's conditions are just right or just shy of life's threshold, a delicate balance that keeps the mystery alive, inviting us to dream of what might be. The search for life on Titan is a story of connection. If life exists there, it would redefine our place in the cosmos, showing that life can thrive in unexpected ways, in worlds far from our own. Even if Titan is lifeless, its chemistry teaches us about life's origins, about the possibilities scattered across the universe. When you look at the night sky, you're seeing a cosmos alive with potential, with moons like Titan holding secrets we're only beginning to explore. Could life exist on Titan? It might, in methane lakes or a hidden ocean, as alien, microbes or something stranger, adapted to a world of ice and haze. But whether life exists, whether it's possible, these remain gentle enigmas, questions that invite us to imagine, to float in the cosmos' embrace. Scientists will keep searching, flying drones, dreaming of submarines, seeking the spark of life on this distant moon. As we leave this mystery, let your thoughts soften, like methane rain falling on Titan's lakes. Titan reminds us that life might be anywhere, that the universe is full of possibilities, connecting us to its wonders. Rest now and imagine that golden moon, glowing softly, guiding you towards sleep. Another mystery awaits, but for now, just drift. Imagine the night sky, a vast canvas of stars, each a beacon in the cosmic dark, stretching across billions of light years. You listen, waiting for a signal, a whisper from another world, a sign that we're not alone. But all you hear is silence, a quiet so profound. It feels like the universe is holding its breath. For decades, we've searched for extraterrestrial intelligence, sending messages, scanning the stars, yet the cosmos remains mute. Why is the universe silent? Are we truly alone, or is there another reason for this stillness? Let's drift into this gentle mystery floating among the stars, letting their quiet glow guide us towards sleep. Close your eyes and picture a radio telescope in its dish turned to the heavens, listening for patterns in the cosmic static, signals that might carry the voice of another civilization. This search, known as SETI, the search for extraterrestrial intelligence, began in the 1960s with scientists like Frank Drake pointing antennas at nearby stars, hoping to catch a deliberate transmission. We've listened across radio waves, optical pulses, even exotic frequencies, but the universe has offered no reply, only the soft hum of its own natural rhythms. Why does this matter? The silence of the universe, often called the Fermi paradox, challenges our deepest hopes and questions about life. With billions of stars in our galaxy alone, many hosting planets, some surely habitable, we expect to find others out there. Yet the absence of signals forces us to wonder, are we the only intelligent life? Is the universe teeming with life, but silent for reasons we don't understand? This mystery is a soothing enigma, a story that connects us to the cosmos, inviting us to dream of distant worlds. Let's linger in this thought, floating in the vastness of space, surrounded by countless stars, each a potential home for life, yet silent in their glow. It's a calming idea, isn't it? That the universe, in its quiet, might be hiding stories we've yet to hear, civilizations waiting to be found, or perhaps a solitude that makes our own existence all the more precious. The silence is a canvas for wonder, a mystery that cradles us gently, urging us to rest in its embrace. Now let's explore the science, softly, like whispering a tale under the starlit sky. The Fermi paradox arises from a simple calculation. Our galaxy, the Milky Way, contains about 100 billion stars, many with planets. Studies from telescopes like Kepler suggest billions of these planets lie in the habitable zone, where liquid water could exist, a key ingredient for life as we know it. If even a tiny fraction of these worlds host intelligent life, and if some develop technology to send signals, we should have heard something by now. But we haven't, and this silence demands an explanation. One possibility is that intelligent life is exceedingly rare. Picture the journey from simple microbes to complex technological civilizations. Life on Earth took billions of years to evolve from single cells to humans overcoming countless hurdles, mass extinctions, climate shifts, and chance events. Perhaps this great filter stops most planets at an early stage, leaving few, if any, worlds with beings capable of building radios or lasers. The universe might be full of life, but silent, because intelligence is a fleeting spark, a rarity in the cosmic night. Another idea is that civilizations exist, but don't communicate. Imagine alien societies choosing silence, perhaps to avoid detection by hostile forces, a strategy called the dark forest hypothesis. Or maybe they use technologies we can't detect, like neutrinos or quantum signals beyond our current reach. Their signals might be too weak, lost in the vast distances between stars, or directed elsewhere, missing Earth entirely. The universe could be buzzing with chatter, but we're tuned to the wrong frequency, listening in the wrong way. Could we be too early or too late? The Milky Way is 13 billion years old, but Earth's intelligent life emerged only recently, a mere blip in cosmic time. Advanced civilizations might have risen and fallen billions of years ago. Their signals faded into the void. Or perhaps they're yet to come, and we're among the first, pioneers in a galaxy still waking up. This temporal mismatch could explain the silence, a reminder that time, like space, is vast, separating us from others in its gentle flow. The search for signals is daunting, adding to the mystery's allure. SETI projects like Project Ozma and the Allen Telescope Array have scanned thousands of stars, but that's a tiny fraction of the galaxy. The universe is immense, and our search is like dipping a cup into an ocean, hoping to catch a fish. Signals weaken over distance, and natural cosmic noise, pulsars, quasars, can drown out faint transmissions. We've also sent our own messages like the Arecibo signal in 1974, but they've reached only a handful of stars, a whisper in the cosmic wind. What kind of signals are we looking for? Scientists focus on technosignatures, signs of technology like narrowband radio, waves or laser pulses which stand out against nature's chaos. They also search for megastructures like Dyson spheres, which might block starlight in distinctive patterns. But these are human-centric ideas. Assuming aliens think like us, What if they communicate through means we can't imagine, or choose not to build at all? The silence might reflect our own limits, a puzzle that invites us to broaden our perspective. The mystery deepens when we consider the possibility of life without intelligence. Planets might teem with microbes, forests, or oceans, but lack creatures with technology. Life could be common, intelligence rare, leaving the universe vibrant but mute. Or perhaps civilizations are short-lived, destroyed by their own technology. Climate collapse, or cosmic disasters like gamma-ray bursts. The silence could be a warning, a quiet lesson in survival, urging us to tread carefully in our own story. Are we alone? That's the heart of the mystery, soft and intriguing. Some argue the silence suggests we're unique, a solitary spark in the galaxy, our existence a precious anomaly. Others believe the universe is alive with civilizations, but distance, time, or choice keeps them hidden. The truth lies somewhere in this vast unknown, waiting for a signal, a discovery to light the way. For now, the question is enough, a gentle enigma that invites us to dream, to float in the cosmos's embrace. Scientists continue the search, using new tools like the Square Kilometre Array and machine learning to sift through cosmic data. They scan exoplanets for biosignatures, like oxygen in atmospheres, hoping to find life, intelligent or not. Breakthrough Listen, a massive SETI project, listens to millions of stars, expanding the search like never before. Each effort brings us closer, but the silence persists, a reminder that the universe reveals its secrets slowly and in its own time. The mystery of the universe's silence is also a story of connection. Whether we're alone or not, the search binds us to the cosmos, to the stars we gaze at, to the questions we share. When you look at the night sky, you're part of this quest, wondering with humanity about our place in the universe. It's a comforting thought, a reminder that our curiosity, our dreams, link us to the stars, even in their silence. Why is the universe silent? It might be because intelligent life is rare, because civilizations hide or fade, because we're early or late, or because we're looking wrong. But the silence itself is beautiful, a canvas for wonder, a question that soothes as much as it intrigues. Scientists will keep listening, scanning the stars, seeking a signal that might one day break the quiet, revealing we're not alone. As we leave this mystery, let your thoughts soften, like starlight fading into the night. The universe's silence reminds us that we're part of a vast, mysterious cosmos, where questions are as precious as answers. Rest now, and imagine those silent stars glowing softly, guiding you towards sleep. Another mystery awaits, but for now, just drift. Imagine the universe, a vast, shimmering sea of stars, galaxies, and infinite darkness, stretching beyond the edges of your dreams. Every twinkling light, every planet, every breath you take, it is made of something. A cosmic recipe that holds the secrets of existence. Yet we know only a fraction of its ingredients. Stars and planets make up a mere sliver, while the rest is cloaked in mystery. What is the universe made of? What unseen forces and substances shape its story? Let's drift into this gentle enigma, floating through the cosmos, letting the quiet glow of the stars guide us towards sleep. Close your eyes and picture the universe as a grand tapestry, woven with threads of matter and energy, each strand a piece of the cosmic puzzle. Scientists tell us that only about 5% of the universe is ordinary matter, the atoms that form stars, planets, and you. The rest, a staggering 95%, is something else. Dark matter, roughly 27%, and dark energy, about 68%. These invisible components, barely understood, hold the universe together, driving its expansion, shaping its fate. Their mystery is a soothing whisper from the cosmos inviting us to wonder, why does this matter? The composition of the universe is the key to its history and its structure, its future. Ordinary matter is our home, but dark matter and dark energy are the unseen architects, guiding galaxies, stretching space itself. Asking what the universe is made of is like asking what we're part of, a question that connects us to the cosmos in a profound, comforting way. A story that cradles us as we drift toward dreams. Let's linger in this thought, floating among the galaxies, feeling the presence of matter and energy all around you, even the parts we can't see. It's a calming idea, isn't it? That the universe is more than its stars, that it holds hidden forces, weaving a reality vaster than we can imagine, yet holding us gently in its embrace. The mystery of its makeup is a reminder that we are part of something grand, a cosmic dance of seen and unseen, waiting to be understood. Now, let's explore the science, softly, like tracing a story across the night sky. Ordinary matter, or baryonic matter, is made of atoms. Protons, neutrons, and electrons forged in the Big Bang and later in stars. This is the stuff of everything tangible. The earth beneath your feet, the air you breathe, the light from distant suns. Scientists measure its abundance through the cosmic microwave background, the CMB, a snapshot of the universe's infancy, and through the formation of light elements like hydrogen and helium, which confirm that ordinary matter is just a small fraction of the whole. Imagine that early universe, a hot, dense sea of particles cooling to form the first atoms, the seeds of stars and galaxies. We can see this matter in the glow of nebulae, the dust of interstellar clouds, the hot gas in galaxy clusters. Yet, when scientists add it all up, stars, planets, gas, dust, it accounts for only 5% of the universe's energy budget. The rest, the vast majority, is something we can't touch or see, a mystery that humbles us with its depth. Dark matter is the next piece, a shadowy substance that doesn't emit or absorb light, yet exerts gravity, holding galaxies together. Picture a galaxy spinning like a cosmic carousel, its stars moving too fast to stay bound without extra mass. Dark matter provides that mass, an invisible scaffold that keeps galaxies from flying apart. Scientists infer its presence from gravitational effects, how galaxies cluster, how light bends around massive objects, a phenomenon called gravitational lensing. Dark matter shapes the universe's structure, a silent partner in its evolution. What is dark matter made of? That's where the mystery deepens, like a dream you can't quite hold. It's not ordinary atoms, not stars or gas, but something exotic perhaps. Particles like WIMPs, weakly interacting massive particles, or axions, hypothetical bits of matter yet to be detected. Experiments deep underground in particle accelerators and in space search for these particles. But so far, dark matter remains elusive. A ghost in the cosmic machine, known only by its pull, its quiet influence. Dark energy is even stranger, a mysterious force driving the universe's expansion to accelerate. Imagine the universe as a balloon, not just growing but speeding up, galaxies racing apart faster with time. This acceleration was discovered in the 1990s, when astronomers studied distant supernovae, finding they were farther away than expected. Dark energy, a kind of anti-gravity, seemed to fill space itself, pushing everything apart, stretching the fabric of the cosmos in ways we don't fully understand. Picture dark energy as an invisible tide flowing through the universe, expanding its boundaries. Scientists think it might be a property of space, linked to the cosmological constant, a term Einstein introduced to balance his equations. Or perhaps it's a dynamic field, like quintessence, changing over time. But its true nature is unknown, and its dominance, 68% of the universe's energy, makes it a puzzle that haunts cosmology, a question that drifts like a whisper in the night. The interplay of these components shapes the universe's story. Ordinary matter forms stars and planets. Dark matter binds them into galaxies, and dark energy drives them apart. Together they create the cosmic web, a network of filaments, walls, and voids, traced by galaxies glowing like pearls on a string. But why this balance? Why 5%? Ordinary matter, 27% dark matter, 68% dark energy. The proportions seem arbitrary, a cosmic recipe we can't yet explain, a mystery that invites us to dream. Could there be more to the universe's makeup? Some scientists propose additional components like new particles or forces hidden beyond our detection. Others explore modified gravity. Theories suggesting dark matter or dark energy might not exist, but gravity behaves differently on cosmic scales. These ideas are speculative, but they add to the mystery's allure, hinting that the universe might surprise us, revealing truths we can't yet imagine. Woven into its very fabric, scientists probe the universe's composition with telescopes, particle detectors, and simulations, piecing together clues from the CMB, galaxy, surveys, and gravitational waves. Missions like the Euclid telescope and the dark energy spectroscopic instrument map the cosmos, seeking to understand dark energy's role. Underground labs hunt for dark matter particles, while theorists model the universe's evolution, trying to balance its ingredients. Each effort brings us closer, but the full picture remains elusive, a gentle enigma waiting to be solved. The mystery of the universe's makeup is also a story of connection. The atoms in your body, the ordinary matter, are a tiny part of the whole, yet linked to the dark matter that shaped your galaxy, the dark energy that stretches your sky. When you look at the stars, you're seeing a universe made of mysteries, holding you in its vast, unseen embrace. It's a comforting thought, a reminder that we are part of the cosmos, woven from its matter, its energy, its secrets. And now, as our journey through the cosmos slowly comes to an end, let your mind drift gently through the quiet corners of the universe. We've wandered through galaxies older than time itself, imagined worlds untouched by human eyes, and asked the impossible, questions that remind us how vast, how beautiful, and how wonderfully mysterious this reality truly is. As you lie there, feeling your body grow heavier, your breath becoming softer, remember that somewhere out there, light from distant stars continues its endless travel, shining through ancient space, reaching places we may never see. Every second, galaxies spin, planets orbit, and the quiet hum of the universe plays on, a cosmic lullaby for any who choose to listen. In the grand silence of space, we find peace. Not everything must be answered. Not every mystery needs a solution. Sometimes it's enough to simply wonder, to be curious, to gaze into the night sky and feel small, yet part of something infinite. Tonight, let those thoughts be your comfort. Let the unknown be your companion, the endless night sky a shelter for your dreams. As you close your eyes, imagine floating beyond the boundaries of our world, past the pale blue glow of Earth, beyond the dusty reaches of the moon, past the fiery surface of the sun, and further still, into the calm, quiet darkness where stars are born, in clouds of cosmic dust, where black holes silently shape the fates of galaxies, and where the soft glow of ancient light paints stories on the canvas of forever. Feel yourself weightless, unbound by time, no longer confined by gravity or worry. Every problem, every question, every restless thought slowly drifts away like grains of sand in the endless cosmic tide. You are a traveler of the quiet, and a dreamer floating on a gentle current between worlds, wrapped in starlight and silence. Remember that you are made of the same materials as those distant stars. The atoms within your body once belonged to ancient suns, long extinguished, their remains, scattered across the cosmos and gathered again in you. In this way, you are infinite, timeless, a small piece of the universe contemplating itself. And that, alone, is a beautiful thing. Somewhere, light travels from stars that died billions of years ago. Their glow, though faded at the source, still moves quietly through the void, unnoticed, unhurried, eternal. In the same way, your thoughts tonight may drift across vast distances within, your own mind visiting memories, hopes, and dreams yet unspoken. Let them float. Let them be carried on the quiet wind of sleep. As we leave behind the great questions of the universe of creation, time, and what lies beyond, remember that wonder itself is a gift. To look up at the stars, to ask why, to dream of distant worlds, and to imagine what might be, is to touch the very heart of what it means to be alive. And so, traveler, as the last of tonight's stories fades into the hush of night, I wish you rest. May your sleep be deep, your dreams bright, and your heart calm. May the quiet of the universe lull you into a perfect peace. You are safe, you are infinite, and you are part of something far greater than you could ever imagine. Good night, fellow wanderer, and may you dream among the stars.